Alright, welcome to today's class. We'll be looking at indices today. An index is a number written as a superscript that tells us how many times a term should be multiplied by itself. On the screen we have x and we have a. Alright, the a is a superscript, so it can be read as x raised to the power of a. So we refer to the x as the base and a as the index. Okay, and the plural for index is indices. So you see where the focus of today's course is. Indices is focused on the index of numbers. Okay, now let's look at the laws for indices. You can call them the laws for manipulating indices. Okay, so the first one would be multiplying indices. If we have x raised to the power of a times x raised to the power of b, we can simplify or bring that to mean x raised to the power of a plus b. We see that our multiplication sign here turns to be positive on this other side, while the superscripts, the indices of both numbers, are added. Okay, so that's how we multiply indices. But first of all, remember the base numbers are same, x are same, before we can now decide to do whatever we're doing with the indices of those numbers. The next one will be the dividing indices. Okay, so if we have x raised to the power a divided by x raised to the power of b is same as x raised to the power of a minus b. So the operation here, which is the division operation, changes to the negative operation, okay, for both powers. So brackets with indices, of course, if you have x raised to the power of a with b in brackets, okay, it's simply multiplying, it's simply both powers multiplying themselves. Alright, so we have x raised to the power of a times b. So for the power of 0, whenever you raise a number to the power of 0, that number equals 1. Any number at all raised to the power of 0 would give us 1. Okay, so we have negative and fractional indices. Okay, so in that case, when we have x raised to the power minus a, okay, that is same as 1 over x raised to the power of a. Okay, so the negative on the index makes it become the denominator of a fraction. So we had x raised to the power of minus a previously, but it's same as saying 1 divided by x raised to the power of a. Alright, so that's it for the negative and fractional indices. We have indices of roots. So when we have x raised to the power of b divided by a, it's same as saying the 8th root of x raised to the power of b. Alright, so the a, which the power, the index is divided by, okay, comes to the left hand side of the expression, but comes not just by itself, but comes with a root sign, okay, to get the root of the expression. Okay, so let's look at examples. We have a first example that wants us to simplify 4a times 2a raised to the power of 2. Okay, if we try to simplify that, we'll be having that expression to be equal to 4 times a times 2 times a, right? And that gives us 4 times 2 times a times a times a if we collect like terms. Okay, so if we solve that, we're going to be having, of course, 2 times 4 is 8. So we're having 8a raised to the power of 3. So we have 2 times 4 to be 8, and then we have 3a's. If we multiply them out, of course, remember from one of the laws of indices, if we have a raised to the power 1 times a raised to the power 1 times a raised to the power 1, is same as saying a raised to the power of 1 plus 1 plus 1, which then gives us a raised to the power of 3. Alright, so a second example would be 2a raised to the power of minus 1 times 3a raised to the power of 2. Okay, so if we try to simplify this or expand this, we'll be having 2 raised to the power of minus 1 times a raised to the power of minus 1, okay, because this minus 1 index multiplies both numbers. Now times 3 times a raised to the power of 2. Okay, if we simplify this further, we'll be getting 2 raised to the power of minus 1 times 3 times a raised to the power of minus 1 times a2 when we collect like terms. Alright, so automatically, because we have a negative index on this number, it becomes the denominator of a fraction. So we automatically turn this to 1 divided by 2 times 3 times a raised to the power minus 1 times a raised to the power 2 will be simplified to give us a raised to the power minus 1 plus 2. We then have 3 divided by 2 times a raised to the power of 1, because of course 1 divided by 2 times 3 is same as 3 divided by 2, and a raised to the power of minus 1 plus 2 is same as a raised to the power 1, because minus 1 plus 2 is same as 2 minus 1. That will give us 1. So we finally have 3a divided by 2. Okay, so next we have 2x raised to the power of minus half times 3x raised to the power of minus 5 over 2. Alright, so if we expand this, we'll be having 2 times x raised to the power of minus half times 3 times x raised to the power of minus 5 over 2. And if we take like terms, we're going to be having 2 times 3 times x raised to the power of half times x raised to the power of minus 5 over 2. If we simplify this, we'll be having 2 times 3 times x. From the law of multiplying indices, we have x raised to the power of half plus minus 5 over 2. Okay, so the multiplication here turns out to be positive. Okay, our base is xx, the same, so that goes. If we further simplify this, then we'll be having 1 over 2 plus, in brackets, minus 5 over 2. Okay, we're trying to simplify these indices here now. Okay, if we simplify that, we're going to be having minus 4 over 2. Okay, so this would give us 2 times 3 is 6, so 6 times x raised to the power of minus 4 over 2, which is same as 6x raised to the power minus 2. Of course, we can also write this as 6 divided by, alright, x raised to the power 2. Okay, that can also be our expression. Let's solve a fourth question. So we have 8x equal to 32, and we're asked to solve this equation for x. Okay, so our first step is to find a way to express 8 and 32 as numbers with the same base number. Okay, so that's the first thing we need to try to do. We can look to get an equal factor for both numbers, and if we look carefully, we have 8, we have 2. 2 should be a very good factor for both of them. Okay, so if we raise 2 to the power of 3, we have 8. If we raise 2 to the power of 5, we have 32. So we can change this expression to 2 raised to the power 3 in brackets times raised to the power x equal to 2 raised to the power 5. Okay, so since we have this already, we have an equality sign here also. It's also for us to assume or take both indices, okay, the ones on both the left and the right, to be equal. Alright, so therefore we can say 3x is equal to 5. Okay, so if we divide both sides by 3, we get to have 3x divided by 3 equal to 5 divided by 3, and the 3 on the left hand side would cancel out, because 3 divided by 3 gives us 1, so we're going to be having 1x equal to 5 over 3, which is same as x equal to 5 over 3. Logarithms. So it's very important for us to pay every form of attention to this, and hopefully we get everything we need to grab. Alright, the logarithm of a number is the power to which a fixed number called the base is raised to give a defined number. Okay, so a quick example that could help us understand what I just said is log 100 to base 10 is equal to 2. Okay, and this is exactly the same as saying 100 is equal to 10 raised to the power of 2. Alright, so if we look at this statement critically, we would realize that this 10, which is the base here, is what is moved to the right hand side and raised to the power of what you had on the right hand side previously. Okay, so what this is whenever you're finding the log of a number, it means you are finding what power you would raise 10 to give you that number. Okay, so there are 5 basic logarithmic laws, and we're going to be looking at them now. Okay, these laws allow us to express equations in different ways. So the first one is the law of products. So here we have log mn to base b is equal to log m to base b plus log n to base b. Okay, so it's simply making us understand whenever we have two elements like this, m times n, okay, we can easily just split them into two by finding the log of each of them, but the multiplication there would then turn into an addition of both logs. All right, so we have the law of ratios. Okay, this one says if log m divided by n to base b, if you have log m divided by n to base b, it's same as, okay, what you have on the right side, log m to base b minus log n to base b. So in the case of the division, we have a negative sign. Okay, so the next one is the law of powers. All right, so if we have log n raised to power p to base b, it's same as, having p log n to base b. So we see that the p here, the power on the left hand side of the equation, is moved to the left hand side of that expression. All right, so we have it as p log n to base b. Okay, so we can always do this to analyze or simplify problems further whenever we encounter them in maths. Okay, so roots, the law of roots. Okay, this says if we have log the 8th root of n to base b, we can simplify that as this 1 over a, which represents the 8th root, was just moved to the left hand side of the expression. So we have 1 over a times log n to base b. Okay, so the very last one we're looking at is the law for base change. Okay, so if you have log n to base a, it's same as saying log n to base b divided by log a to base b. Okay, so it's going to be same except for the fact that we have changed the base. So if you look on the right hand side, you have the base changed to b, while on the left hand side it was previously a. But then to do this, of course, we find the log of that number to base b, and then find the log of the previous base to base b, and divide both expressions, and we're going to have a new number with the base change. Now, it's very important for us to know that whenever we have the logarithm of a number, when we have that final answer, that our final answer is divided into two parts. Okay, it has the integral part and has the decimal part. Now, this integral part is called the characteristic, while the decimal part is called the mantissa. And the integral part can be positive, it can be negative, it can be zero. Okay, we have to always remember that. The integral part can be positive or negative, and it can always also be zero. While the decimal part is a real number from 1 to less than 10. Okay, decimal part is always a real number from between 1 and 10. Okay, so we have an example here of a number 1.4114. So we have the first part to be our characteristic, in this case, which is 1. Okay, then we have the decimal part, the other part to be our mantissa. So we have a characteristic of 1, we have a mantissa of 0.4114. If you add both of them together, of course, you see you're going to get the number which you have on the screen. It's very important for us to put our numbers in standard form. It's one of the first things we do when we have a number and we want to find the log of it. And that's because it's a very easy way to spot our characteristic. We talked about the logarithm being divided into two parts, the characteristic and the mantissa. So if you can move your number from the form it's at to the standard form, you can easily spot your characteristic, and that's one part of your problem solved. So what's left is for you to find your mantissa. Okay, so if you have any positive number n in decimal form, it can be written as n equal to m times 10 raised to power p, and then we have this criteria that must be met. P must be an integer, okay, and m must be greater or equal to 1 but less than 10. Okay, so once you have a number in this form, m times 10 raised to power p, and then it meets this criteria, what you have then is your number in standard form. Okay, so let's look at the first example. Write 3.7 in standard form. Alright, so our n here is 3.7, and we're about to give it the form of m times 10 raised to the power p. Okay, so we remember the two criteria that is supposed to our standard form is supposed to meet. So first of all, we have to find m. Okay, so you just saw a previous slide, and on that slide, for us to get our m, we have to consider that the first two non-zero digits. Okay, and we have to find a way to put those digits in a way that they're going to be equal to or greater than 1 but less than 10. Alright, so with this first example, we have 3.7. So how do we present 3.7 in a way that it's equal to or greater than 1 but less than 10? If we try to present it as 0.3, that's going to be less than 1. What if we join both numbers together to have 37? That will be greater than 10. So you see, the best way we can present this to be in standard form would be leaving it at 3.7, because 3.7 is greater than 1 but less than 10. Okay, so we have our standard form to be 3.7 times 10 but raised to the power of 0. Okay, so if we multiply these two together, we're going to still get 3.7. So it's the same number but in standard form. Alright, so the next one we have is 3,700. So the same thing, if we wanted to put this in standard form, we have to get our m to be 1 or greater than 1 but less than 10. And so you see that we still don't have a choice than to take 3.7. So 3.7 it is, and we're going to have 3.7 times 10 raised to the power of 3 in this case. Let's look at another one, 62.723. The same thing, the first two non-zero digits, and that's 62 in this case. So how do we present it to have it between 1 and 10? Okay, if you take 0.6 less than 1, 62 greater than 10, so 6.2 we deal with. Alright, so in that case, we're going to be having 6.2723 times 10 raised to the power of 1. Alright, the raised to the power of 1 represents the change in the decimal position. So if we multiply that out, we still get 62.723. Okay, let's take the fourth one, and I think the last one, 0.002385 in standard form. Okay, our m in this case, of course, we have to take the first two non-zero digits, and if we look at that very well, we'll see that is 2 and 3. Okay, so if we want to present that to be between 1 and 10, it has to be 2.8. So our standard form will be 2.385 times 10 raised to the power of minus 3. The characteristic can be found by just staring at the number after it has been put in standard form. So you see why it's important you put your number in standard form, so you can quickly pick up your characteristic. Now, looking at the numbers we have in the table here, we have 4 numbers in the table. It's 2.753. If we put that in standard form, we have 8.2753 times 10 raised to the power of 1. Now, automatically, our characteristic is 1. Okay, that can be easily seen. Then the second one, 0.25892, in standard form is 2.5892 times 10 raised to the power of minus 1. Automatically, our characteristic is minus 1. Now C, 246.21. Putting it in standard form, we have 10 raised to the power of 2. Therefore, our characteristic is 2. The same thing with D, 0.0009248. Putting it in standard form, we have 9.248 times 10 raised to minus 4. And minus 4 is automatically our characteristic. So you see, once you put your number in standard form, you can quickly pick up your characteristic, and you know what you have left to find is your mantissa. Okay, so to prove this theory, let's get a random number. Okay, this is an example we had done before, 3.7 times 10 raised to the power 3. We changed 3,700 to a standard form to get this. Okay, so let's try to prove that integral part and the mantissa. We're to find the log of this. We'll be having log n to base 10 is equal to log 3.7 times 10 raised to the power 3 to base 10. Now, if we go further, we'll see from the law of products that log n to base 10 is same as log 3.7 to base 10 plus log 10 raised to the power 3 to base 10. Alright, so also from the law of powers, we would see that we have the 3, the 10 raised to the power 3. The 3 on that 10 can be brought down to the left hand side of the expression, so we can have 3 log 10 to base 10. Okay, so if we further simplify this, we automatically have 3 plus log 3.7 to base 10. Alright, so that's there is a combination of two expressions to give us the log of n. So you can see 3 there. That 3 represents our integral part, while the log 3.7 to base 10 is the mantissa, okay, of the logarithm expression. Okay, so we already have our characteristic as 3, so we keep that aside. We find the mantissa and then we add both of them together to get the log of the number. Okay, so this is just a proof of what we talked about. So let's also look at the second one, 2.385 times 10 raised to the power of minus 3. If we find the log of that number, we're going to be having log 2.385 times 10 raised to the power of minus 3 to base 10. From the law of products, we have that can be log 2.385 to base 10 plus log 10 raised to the power minus 3 to base 10. We use law of products to bring the power for 10 down to the left hand side of the expression, and then we have minus 3 plus log 3.7 to base 10. So here we have another log that's giving us two different expressions, one for our characteristic and the other one for the mantissa. Okay, we would later on find out that when we are trying to add the both expressions together, that's the characteristic and the mantissa. If we have a negative characteristic, we don't use that operation in the addition. We just represent the negative as a bar up here, but we'll get to that when we'll be finding the mantissa, as that's what we'll be doing next. Finding the mantissa. The first step to finding the mantissa will be for us to take the first 4 significant figures, okay, from the numbers we have. Okay, and this is the first 4 digits from the left, starting with the first non-zero number. Okay, so we don't have to consider the decimal. Okay, we just count from the first digit on the left that is not a 0. Okay, count from there downwards, pick up the first 4 numbers, and we move on to step 2. So if the significant number happens to just be 1, we add a 0 to the right hand side so we can have 2 digits, because we need a minimum of 2 digits to read off values from the table. Okay, so once we do that, we move to step 3. We head to the logarithm table with our digits, the 4 digits or a minimum of 2 digits to get our readings. Okay, so let's take examples. The first example we'll be taking is find the log of 5295 from tables. To do that, we'll have to put our number in its standard form. Okay, so if we do put that in standard form, we'll have 5.295 times 10 raised to the power 3. So we move on. From what we have already, we can see that our characteristic is 3. Okay, but of course, we can just go ahead to prove how we got 3, or to be sure that yes, it's 3. Okay, so log 5295 to base 10 is equal to log 5.295 to base 10 plus log 10 cubed to base 10. If we simplify this, okay, we're going to be having log 5.295 to base 10 plus 3. If we then move ahead to rearrange this, we're going to have the next line. Okay, now we head to the tables with our 4 significant digits. Okay, so we can see that our characteristic here is 3 and our decimal part is log of 5.295 to base 10. Okay, so we head now to our log tables with our significant digits. Okay, so our significant digit is 5295. We can see that it's actually even the same thing with what we have here. All right, so we didn't need to go through all these steps, but I mean, anybody who wants to do this step can do it. But from here, we could easily just pick our 3 as our characteristic and then take up our significant digits and move to the logarithm table. So going into the log, we look for the row that has our first 2 digits. Okay, and that's 52. So we look for row 52. Once we get row 52, we look for the column that has our 3rd digit, which is 9. Then we read the cell where column 9 coincides with our row 52, and the value in that cell is 7235. Okay, then we read the column in the mean difference section. We read the column that has 5 written in it because that's our 4th digit. So once we do that, once we see the column, we read off where that column coincides with row 52, and we would have the value there to be 4. So if we add it to what we had previously, we would have 7235 plus 4, which is 7239, and that gives us our mantissa. Okay, so we add our characteristic to the mantissa. If we do that, we're going to get 3 plus 0.7239. Remember, the mantissa is the decimal part. So once we do that, we're going to get 3.7239. Okay, so we look at another example. Find the log of 0.25795 from tables. So what we do, we put it in standard form. Of course, from this standard form, you can see that our characteristic is -1. Then we move on to the tables. Our significant digit is 2579. That's the first 4 significant numbers. So we have it as 2579. So we look for the row 25 on the log table, then look for the column that has 7 written in it, and read off the cell where row 25 coincides with the column 7. And if we do that, we'll have 4099. Then we go to the column of mean differences, read where row 25 coincides with column 9 in the mean difference section, and we would have 15. So if we add 4099 to 15, we would have 4114 as our mantissa. Okay, so it's good to remember that whenever we have a negative characteristic, we don't carry out the negative operation. What we do is to put a bar above the characteristic to signify that it's negative. So if we do that here, we're going to be having bar 1 plus 0.4114, which will give us bar 1.4114. Okay, we can be given the logarithm of a number and asked to find that number. So for example, we have log 5295 to base 10 equal to 3.7239. We're now asked to find the antilog of 3.7239. Okay, that would give us 5295. So it's like doing the reverse of what we did in finding logarithms. Okay, so let's look at using logarithm tables to get our antilogs. Okay, so the first step to finding the antilog of any number is noting if the decimal part is positive or not. Okay, so if the decimal part is positive, we move to step 2. But if it's negative, we make it positive by adding 1 to the decimal part and by subtracting 1 from the integral part. Alright, so for an example, we have a question asking us to find the antilog of -2.2973. Alright, we can see that if we separate the number into its integral and decimal parts, that the decimal part is negative. Okay, because we'll be having -2 minus 0.2973, and that's the only way we can add these two numbers to get -2.2973. So if we split them like this, we find out that our decimal part is negative. So therefore, we can't move on to step 2 yet. We have to add 1 to the decimal part and subtract 1 from the integral part. So if we do that, we're going to be getting -3 plus 0.7027. Okay, which would give us -3.7027. Okay, so for our example in step 1, if we go to the logarithm tables as step 2 says, okay, so we have, first of all, we have 0.7027 as our decimal part. So we take the first 2 digits, okay, that is 0.70, okay, that's 0.770. We take those first 2 digits into the logarithm table and we look for the row containing it. Okay, so once we get that, we now read off the value in the column headed by the 3rd digit, which is 2. Okay, remember our decimal part is 0.7027, so the 3rd digit there is 2.702. Alright, so if we do that, we're going to be having our answer in this step 2 to be 5035. Okay, so let's go to step 3. So we go to the column of mean difference and we read off the value in the row with our 4th digit as header. Then add this value to our number gotten after step 2. So our 4th digit here is 7.7027. The 4th digit there is 7. So we go to the column of mean differences to read off the value of 7 that collides with that row we're working with. That's the row that has 0.70. Okay, so if we do that, we are going to have 5035 plus 8 because the value of the mean difference we're using is 8. So if we add 8 to the previous number we got, we're going to be having 5043. All right. So fourth step, we add 1 to the characteristic of the number gotten in step 1, then use the value gotten to add a decimal point to our answer from step 3. Okay, so our characteristic, okay, that's the integral part, which we got in step 1 was -3. Okay, so if you add 1 to it, we're going to be having -2. So our final answer will be 0.00504. Okay, note that from the tables, the values we get have the decimal point before the digits. Okay, so because of that, we are moving our decimal place 2 steps to the left. Okay, because we have -2. So our decimal place was before 5. We're moving it 2 steps to the left. So we're going to have 0.005043 because the decimal point moved 2 places, 1, 2. All right. Okay, so let's go into multiplications and division with logarithm. All right. Our first example will be evaluate 2.413 times 3.092. So if we use tables to find the individual logs, we would have them as 0.3825 and 0.4903. So we raise 10 to their powers, which will give us this exact number. Okay, so 2.413 is same thing as 10 raised to the power 0.3825. If we simplify this, remembering the law of indices, the law of powers, okay, we will have 0.3825 plus 0.4903, and then we will finally have 10 raised to the power of 0.8728. Okay, so now we find the antilog for 0.8728 exactly the same way we did previously. So remember, from step 1, we separate our decimal from our integral part and then confirm that our decimal part is non-negative. If it's negative, we do what step 1 says. If it's not, we move on to step 2. So if we do all that, we'll get our mantissa to be 7461. Okay, and remember we said that whenever we get our answer from the log, from the antilog chart, that this number is actually 0.7461. Okay, so our characteristic is 0. So we add 1 to our characteristic to get the number of decimal places. We are moving the decimal 2 from where it is. So that means 0.1. So 0 plus 1 will give us 1. So we're going to place in our decimal point 1 step to the right. Okay, so our answer will be 7.461 because we have moved the decimal point from before 7 1 step to the right. So we get 7.461. Okay, so next example would be evaluate 45.80 divided by 6392. Okay, so if we use the tables to find the individual logs like we did before, we find them, then raise 10 to their powers to give us exactly the same numbers. Okay, so we do this, simplify it, and we have 10 raised to the power of 0.8555. Okay, so now we find the antilog of 0.8555. We get our mantissa as 7166. Okay, so again, to get the antilog of 0.8555, if we separate our integer from the decimal part, we'll be having 0 plus 0.8555. Okay, so our decimal part is positive. So we just take the first 2 digits, which is 0.85, into the tables. So read off the value that coincides with the column that has 5 on it. Okay, because our 3rd digit is 5. Okay, once we get that answer, we go to the column of mean differences and read off the column that has 5 written on it and coincides with the row of 0.85. So if we do that, we're going to have 7166. Okay, so since our characteristic is 0, we add 1 to it and use it to place our decimal point. So if we do that, we're going to have 7.166 in this case because we are moving our decimal place 1 step to the right. All right, calculating powers and roots with logarithms. So for an example, we have 5.103 raised to the power 3. How do we simplify this to solve this using logarithm? Okay, so we use the table to find the log of 5.103. Okay, so once you get that, we now find the antilog of whatever it is we got. Okay, so if you look here closely, you'll see we have 2.1239. Okay, so we are taking out the decimal, we are finding the antilog of the decimal part. Okay, our integral part is 2, the decimal part is 0.1237, so that's why we have 0.1237 here. So if we get the antilog, if we go into the tables, look for the row that has 12, then look for the column that has 3 written on it. Read off the cell at the junction where the column of 3 meets with the row of 12. Okay, once we read off that value, we go to the column of mean differences, read off the column that has 7 written on it, because that's our 4th digit. Okay, read off that column where it coincides with the row of 12, and we also have our mantis, and we'll have that to be 1329. Okay, so since our characteristic is 2, we add 1 to it, and we're going to be having 3. So we're going to move our decimal place 3 steps to the right. So if we do that, we're going to be having 132.9. Okay, so another example will be evaluate the cube root of 26.21. So we go straight to find the log of 26.21. If we do that, of course, we'll get 10 raised to the power 0.473. We find the antilog of 0.473. We do that, we get our mantis to be 2972. Okay, since our characteristic is 0, we add 1 to it. So we'll be moving our decimal place 1 step to the right. So we'll have 2.972. Alright, so we can solve these same problems in tabular form. Okay, so we're going to do that for the examples we just did. We're going to redo them in tabular form. So the first one is evaluate 2.413 times 3.092. Okay, so if we do that, we can have this kind of table: 2.413 times 3.092. We find the log of 2.413, we find the log of 3.092, we add them together to get 0.8728, then find the antilog of 0.8728, we are going to get 7.461. So we do that for the next one, 45.80 divided by 6.392. If we find the log of 45.80, we have this. We find the log of 6.392, we have this. We subtract both of them together to get 0.8555. We find the antilog of this, we get 7.166. So we'll do that for the third example, 5.103 raised to the power 3. We find the log of 5.103, we have 0.7079. Okay, we multiply the log we got by 3 to get the value of 5.103 cubed, we get 2.1237. We now find the antilog of this to get 132.9. So we do that for the last example. Alright, we have the cube root of 26.21. So we find the log of 26.21, which gives us 1.4185. Okay, so of course we multiply this by 1 over 3. If we do that, we're going to have 1.4185 times 1 over 3, which is same thing as 1.4185 divided by 3. If we do that, we're going to get 0.473 as our answer. So we find the antilog of 0.473 and we get 2.972.